Welcome, everyone. For today's prep, we're going to start to look at the idea of net change, and we're going to do this in the context, for right now, we're going to come back to these, but we're going to look in the context of motion in a straight line. So we know that when an object's moving in a straight line, there's kind of three important functions that we've considered. The position function, s of t, the velocity function, v of t, and the acceleration. So for this, we're going to be looking at just our velocity and our position. And the question we're going to investigate here is what happens if we integrate the velocity function over some time interval going from a to b? Well, we know our velocity function is just the derivative of the position function. And when we're integrating a derivative, essentially the integration and the derivative part cancel each other out. So we just have the evaluation then of our position function. So the top number goes in first, and then the bottom number goes in second when we do our evaluation. Okay, so what is this? What are we getting here after we do this? So A is the start time. So we're investigating our object over a time interval going from A to B. So A is the starting time for that time interval, and B is the ending time. So when we calculate this difference here, we're taking our end position. So this is where our object ends up after it does all of its traveling, and we're subtracting off its start position. So if we do this subtraction between its ending position and its starting position, we get what's called the displacement. And that's what this is. So displacement measures the distance and direction between the starting position of our object and the ending position of our object. So it's possible with displacement that you can end up with positive values, negative values, or you can end up with zero. So displacement can be positive, 0, or negative. So what happens if displacement is 0? Well, that means your end position matches up exactly with your start position. So your object's moving around, and during this time interval, it moves, and then it gets back to exactly where it started. So its start and end position are the same. If the displacement is positive, well, then the net effect here is that our object's moving around, and during this time interval, it's ultimately moved further in the positive direction. So if displacement's positive, it's moved in the positive direction, and if displacement's negative, then it's moved in the negative direction. All right, so what we've seen is displacement. We can calculate this by just integrating our velocity function. Now, the question is, integrating our velocity function gives us displacement, but it doesn't tell us exactly how far our object's moved. So our object's moving around, and it's possible with displacement that you could end up with zero displacement. And that doesn't fully convey the whole story of if our object's moving around and it starts somewhere, moves around a bit, and then comes back, it doesn't tell how far it's actually traveled. So another reasonable thing to kind of want to know is the total distance traveled. And so this measures the total distance traveled by our object during the time interval, and we don't really keep track of the direction. We just want to know how far did it actually go. So we can calculate total distance by integrating. And with our velocity function has kind of two components. There's the size, the magnitude of it, which describes how fast our object's moving, but then there's also the direction component, so positive or negative. moving in positive direction or negative direction. So how do you get rid of the direction information? Well, you do the absolute value. So if we integrate the absolute value of the velocity function, we get the total distance. So with displacement, you can kind of have some canceling. So if you're moving in the positive direction and then you move in the negative direction, they can kind of cancel each other out. But if we do the absolute value of the velocity function, well, we're not going to have that canceling anymore. So we can do this to kind of capture the entire total distance that we've traveled. Now, as we've seen, integrating absolute value, though, is difficult because absolute value is a piecewise function. So we have to kind of split this integration up based on where our object, or when our object, is moving in the positive direction and when it's moving in the negative direction. So as a little example here, here's a graph of just some velocity function. And we can see that for a certain section, the velocity function is above the t-axis. So what this is telling us is that during this time, our object is moving in the positive direction because velocity is positive. So going from time 0 to time c in this case, our object is moving in the positive direction. Now going from time c to time d, now our velocity function's negative, so this must mean we're moving in the negative direction. So what we're going to do, how we handle the absolute value here, is we're going to figure out the distance that our object travels going in the positive direction. And then separately, we'll figure out the distance that it travels going in the negative direction. And once we have these two separate distances, we're going to add the results together. Now, it turns out, going back to displacement, we can kind of interpret displacement now in terms of moving in the positive direction and moving in the negative direction. So we can figure out displacement by figuring out the distance that we travel in the positive direction, and then subtract off the distance that we travel going in the negative direction. So just as a quick example, if I were to looking at this graph here, to me it looks like the distance that we're going to be traveling in the positive direction, the size of this is going to be larger than the size that we're traveling in the negative direction. So I would expect, if I were to calculate the displacement here, I would expect the displacement to be positive, meaning we've traveled further in the positive direction. All right, so let's try an example of this. And let's do part 1. So we have a rocket that's fired vertically into the air, and its velocity at t seconds after liftoff is given by this velocity function, negative 32t plus 160. The units here are feet per second, and we're looking at the time interval going from 0 to 8. So displacement, nice and easy to calculate. We can just do the definite integral of our regular old velocity function. So the displacement over this time interval going from 0 to 8 is going to be the integral from 0 to 8 of just the velocity. And if we fill that in, our velocity function is negative 32t plus 160. And this is just a definite integral. So we want the antiderivative of that first piece. We get negative 16t squared. We do our power rule. And then the antiderivative of that second piece is 160 times t. And then we're going to evaluate this going from 0 to 8. All right, so we do the evaluation, set up our parentheses. Probably need a little bigger. top number gets plugged in first. So plug in 8, and we get negative 16 times 8 squared. And then we plug in 8 here, we get 160 times 8. And then when we plug 0 in, we get some powers of 0. So just 0. Okay. And perfectly fine to just leave your answer like this. Trying to think if I can simplify it. Maybe I can. I don't have my calculator here. So we could factor out, let's just see. I'm kind of curious what we get. So if we factor out 16, actually 16 times 8. So we get 16, factor out the 8. And what we're left with here is a negative 8. And then what we're left with here is just a positive 10. And if we simplify that, negative 8 plus 10 is positive 2. So we end up with 16 times 8 times 2, which is 16 squared. All right, so again, perfectly fine if you just wanted to leave it like that, though. All right, so what are the units, though, for displacement? Well, we know our units for velocity here are feet per second. So the units of distance here are given in feet. So our units for this are feet. Okay, so that one's not too bad. Displacement's not too bad. We just get to integrate our velocity function. Now, how do we find the total distance traveled by our object? So the issue is the graph of this velocity function is, well, this graph right here. And what happens is we have, as we mentioned, we have this section where it's traveling in the positive direction, but then the velocity becomes 0. So our object stops moving, and then it starts to move in the negative direction. So part of this is going to cancel off the gains we made going in the positive direction. So the displacement isn't capturing how far we've actually traveled. It's only capturing the difference between where we started and where we currently are. So the idea here with getting total distance is we're going to figure out the distance we travel going in the positive direction, and then we're going to separately figure out the distance traveled going in the negative direction. And if we're looking at this graph, we can see that our velocity is 0 at t equals 5. So when we do this, we can find some we want to look for the intersection points. When is our velocity function 0? When does velocity cross the t-axis? So the idea here is we're going to set v of t equal to 0 and solve for t. And based on the graph, we kind of can tell that it's 5, but let's just confirm this with some algebra. So we're going to take our velocity function and we're going to set that equal to 0 and solve for t. And we can just directly solve this one. So if I add 32t to both sides and then divide by 32, I get t is equal to 160 divided by 32, which is 10 divided by 2, or 5. All right, so at time 5, this is when our object stops moving. So then we can kind of go through and just investigate the intervals a little bit. And then we could probably just do this from the graph, but if we didn't have the graph, so our time interval is we're going from 0 to 8, and we plot our intersection points, so when the velocity function was 0, so in this case 5, and what this does is it splits up our time interval into two sections. We have this section going from 0 to 5, and then we have this section going from 5 to 8. And we know, based on our velocity function, that our velocity function is positive on that first interval and then negative on that second interval. So this means on this first time interval, we're traveling in the positive direction, and on the second interval, we're traveling in the negative direction. So we're going to split up and do two separate integrals. We're going to first integrate from 0 to 5, then we're going to integrate from 5 to 8. All right, so let's do our two integrals. Integral from 0 to 5. We're going to integrate our velocity function, and our velocity function was negative 32t plus 160, and we already found the antiderivative of this, so negative 16t squared plus 160t, and then we're evaluating from 0 to 5 in this case. And when we do our evaluation, we end up with negative 16 times 5 squared plus 160 times 5, and then we subtract and plug the 0 in, and again, kind of get a freebie here, just some powers of 0. So just a 0. All right, so the next integral we're going to do is we're going to integrate from 5 to 8. So we want to do the other integral. Same velocity function. So we're going from 5 to 8. Same velocity function, just a different time interval here. So that means the same antiderivative, negative 16t squared plus 160t. And now we're going from 5 to 8. All right, so if we plug in the 8, plug the top number in first, and we get negative 16 times 8 squared plus 160 times 8. Then we subtract, and then we plug in the 5. So we get negative 16 times 5 squared plus 160 times 5. All right. So what are these values? We gotta do some interpretation. So this integral here is the integral from over this positive interval when we're moving in the positive direction. So this value is positive, and what this value represents, this represents the distance that we've traveled going in the positive direction. So it's our distance that we've traveled going in the positive direction. So this is a positive value here, if we were to simplify that down. Now, the second value, though, if we were to simplify this down, this is going to be a negative value. And why is it negative? Well, because we integrated our velocity function. We haven't made any changes yet. And on this interval, going from 5 to 8, our velocity was negative. So to get the distance traveled in the negative direction, we're going to have to negate this. We're going to have to do the absolute value of this. So the distance traveled in the positive direction is the integral going from 0 to 5 of our velocity function, because that's when our object was moving in the positive direction. And the distance traveled in the negative direction is, it's not quite this integral. This integral is doing most of the work for us, but we just have to do the absolute value. We have to we have to do a double negative, essentially. So we're integrating from 5 to 8 of this velocity. And so then to get the total distance, we're going to add these two values together. So we're going to add our total distance going in the positive direction and add to it the total distance going in the negative direction. All right, so we're going to actually finish this example up in class. So I want you to just see what these values are, kind of as part of the prep. I want you to simplify this value down, see what you get. You should see that it's positive. And then you simplify this down, which we already did. This should be 16 squared. But again, simplify this entire thing, see what number you get. It should be negative. And so that negative is kind of like the direction. So it's telling us how far we traveled, and the negative just tells us we've gone in the negative direction. So add the result from here, make this result positive, and then add the two together. See what you get. And we'll go through the answer in class. So we'll see you then. Bye-bye.